Good morning, or good afternoon, or good evening, depending on when are you watching this talk. This is
Buenas tardes, Montero.
and myself, Mark Manera, and we are going to tell you about the DESI-DR2 results, or in other words, from Baryon Acoustic Oscillations to evolving dark energy. Let's start. This is what we will cover. We'll talk about the instrument, the Dark Energy Spectroscopic Instrument, give you a basic introduction of the Baryon Acoustic Oscillations, and then we will move about the measurements from DESI on galaxies and Lyman-alpha forest, and finally we will talk about the cosmological results in relation to dark energy, the Hubble tension, and the neutrinos. So let's start with DESI. DESI is a multi-object spectrograph instrument which is mounted at the 4 meters Mayor telescope. DESI is the first stage 4 experiment on the sky. And now we also have Euclid, which has been running for more than 1 year, and Rubin, which is starting right about now. DESI started its 5-year campaign on the 15th of May 2021, which means that we already are at the 5th year of observations. And this talk will be, though, about the 3rd year of observations, which we call data release 2. Also, DESI will be extended a few years, so we'll have a lot of more data coming also. Now, let's start by thanking our sponsors and participating institutions. We have 72 participating institutions and more than 1,000 scientists working on DESI, so we thank all of them. And go back to the telescope. So this is a picture of the telescope. It is still at Kitt Peak at the Mayor telescope, as I mentioned. We'll observe an order of magnitude more galaxies than BOSS and eVOSS. And this is how the telescope works. The instrument works. We have at the focal plane, we have 5,000 fibers that are mounted in some robotic actuators. And these collect the light from the galaxies that are focusing on these fibers. These robotics can move around like 12 millimeters to place themselves where the image is formed. And then these fibers are collected in 10 fibers coupled bundles to spectrograph, where we take the spectra. And the combination of having 5,000 fibers and 3 degrees field of view makes this experiment very powerful, and that's why we have a lot of data. So this is how the positioner or the robot looks like, and it can patrol around like 1.4 arcseconds. And this is how the focal plane looks like with the 5,000 fibers. And in a circle, you have the guiding, focusing and alignment camera, which is the in-kind hardware contribution that 25 have contributed to DESI. So this is one of our contributions, the hardware one, and this is the image. And here you have the people that were involved in this. And also in EFI, you have 4 people who are DESI builders. So there's 1 camera of this for each petal, so it's a total of 10 cameras. Now, with this awesome instrument, we are going to observe 4 million galaxies at different redshift. So we have bright galaxy survey at lower redshift, and then we will observe luminous red galaxies at 13 million of them within 0.1 and 0.4 in redshift. Then we'll observe emission light galaxies, 8 million of them, and at higher redshift, 3 million quasars. And we also have Lyman-alpha forest. This is how the data release 1 looked like. That was 1 year of observations. And you see here in the sky, the footprint and the area that was observed. In colors, you see the number of tiles that were covering each of the points in the sky. And you see what was the status like a few years ago. And now this is the area that we have observed. So we have a much more coverage right now. And even if the 3 years observation, this is more than 60% of the data, 67% of the fiducial expected data collection. So once we have this, we now can move to what we can do with this data, with all these spectra of galaxies that we have collected.
So the most important cosmic proof that we are going to discuss today, that is the one that was measured with all these beautiful DESI data, are baryonic acoustic oscillations. With baryonic acoustic oscillations, we refer to sound waves in the primordial plasma. That was when the universe was very hot and dense, and we had baryons and photons coupled together. These sound waves were generated by the combination of gravity and pressure, and we can see in the video we had multiple sound waves happening in different places of the universe. These were traveling and then they stopped at a distance of around 100 megaparsec over H and left a pattern imprinted in both the cosmic microwave background and also in the distribution of galaxies. That this is what we are going to use in order to do cosmology. So as you can see in the video, there are multiple points on top of the distribution of that we consider all the different oscillations. And these are the galaxies that we measure. So what we do in DESI is to compute the typical distance between different galaxies, as you can see here, and just plot an histogram for all the different separations. And what we find when we do that is that at very small scales, the probability of finding galaxies is larger, then it goes down, and at around 100 megaparsec over H, as I was mentioning before, we have a peak, an excess in the probability of finding galaxies, and this is precisely the BO peak. You can see it. And this is just a plot showing this peak in the real distribution of galaxies of DESI. And we can see this excess, and what we do in DESI is to measure the position of the peak. This is encoding cosmological information. So what we can do is to measure this position of the peak for different recipes, and because we know that the size of the peak should be around 100 megaparsec over H, we can treat it on a standard ruler. So we know what will be the size and what is the size that we really measure in the distribution of galaxies. In this way, we calibrate it in the same way that it is done with supernovae with their brightness. So what is the cosmological information encoded in this feature? Along the line of sight, we are mostly measuring the size of the sound horizon at the time of Dark epoch, when was the decoupling of the baryons and the photons, divided by C over the Hubble parameter. And perpendicular to the line of sight is again the sign of the sound horizon divided by the angular diameter distance. As you can see, the Hubble parameter that is here is just as a function of Hubble parameter at resist 0, and also the amount of matter in the universe and dark energy, and perpendicular to the line of sight is just an integral of this parameter. So in the end, all the cosmological information that we are measuring is the product of the sound horizon and the Dark epoch times the Hubble parameter, resist 0, and the amount of matter in the universe. And it is very important to do this measurement of the BO peak at different resists because the degeneracy between these parameters changes as a function of redshift. This is what we can see here from very low redshift, BGS, up to very high redshift, the Lyman-alpha forest. We can see that the different posteriors are rotating to the left. And now Mark is going to discuss all the measurements of the BO peak that we do in DESI with galaxies and Lambda.
So let's just start by saying we have different galaxy samples, and we split also these samples in redshifts. So we have different redshift bins that cover from 0.1 to higher than 2. And as you see here, I put on the right several numbers for galaxies of each bin for the DR1 data. And on the main table, you see the numbers for the actual release. And what you are seeing is that, for instance, if you look at LRG1, large luminous red galaxies bin 1, from 0.4 to 0.6, you have 1 million galaxies in this case. And it's double the number of the data release 1. So we have within 2 and 3 times more galaxies, and we have these bins. Also, you notice that there is a bin that combines LRGs and ELGs by weighting appropriately the clustering amplitudes. And this is the first time that this is done as a single beam, well, also in DESI. And then also this, because we have this number of galaxies, and as I mentioned before, every galaxy is observed at a particular point in the sky. You have to add some weights to make for completeness and observational and systematic effects. So once you do this, you can complete the correlation function, and it shows the isotropic and isotropic part of it, the monopole and the quadrupole. And for this, we fit the VAO peak. The VAO peak is fit to the reconstructed two-point functions, which means that we have removed some of the nonlinearities by moving galaxies back to their linear positions and then get a more prominent peak. This is a technique that has been going on for more than 10, maybe 15 years. So it's a standard technique. And also, this analysis was blind, meaning that to avoid confirmation bias, we have at the level of catalog, move the galaxies to shift the cosmology. So while we are analyzing this, we don't know the cosmology that the data gives us, and then we unblind and we have the results. And all these proceedings in methodology has been tested with some validation tests. You here have some list of the validation that has been happening. This includes modeling, beams, reconstruction, and so on. In particular, you can see what happens if you don't weight galaxies. You can see what happens if you have analyze only different parts of the sky, or if you cut your sample in different mass or magnitude beams. And this allows us to control the level of systematics, and we see that the systematics are subdominant with respect to the signal that we have, to the statistical error that we have. And now this is a summary of the results. You can see at the top panel, the isotropic VAO distance against the fiducial or the best fit in the Lambda CDM model. So this will be the line of 1. And at the bottom, you see an isotropic VAO distance again against the best fit. And each of the plots shows a different sample and redshift beam. And we can compare, first of all, the plots that are solid and the points that are solid with the points that are not so solid and in color. And therefore, this gives us the difference between year 3 and year 1. So the solid ones are the results now, and you see you have a smaller error bars, but they are compatible with the results that we had before. Now we can move to look at this in more detail. For here, we have the galaxies from the white galaxy sample, and you see how is the result. And this implies a constraint in the plane omega matter and H naught RD, the Hubble constant times the scale, horizontal scale at the Dark epoch. And you can see that basically here, what is measured is H naught times RD, which if you see the equations that Jonas has shown before, if you were going to at redshift 0, this will only measure H naught. So now we are not exactly H0, but we have mostly measuring H naught RD. Now, when we have different redshift, the degeneracies change direction slightly, so the ratio between omega matter and H naught RD changes. And when we keep adding points, what we see that this allows us to break, in some senses, degeneracy and constrain better the results. So at the end, what we are having is that because they are consistent to each other and they are complementary, we can combine them, and the combination gives us a value for omega matter of 0.2975 and matter on H naught RD of 101.54 times 100 kilometers per second. So this is a 0.7% measurement. Of course, all this is taking into account that we are in the Lambda CDM model. Now we can compare these results with the CMB results for constraints in the same plane. In this case, the CMB plotted in pink shows the primary CMB from Planck and also CMB lensing from Planck PR4 and ACT. And you can see that here in the plot, the results for CMB and the DR1. Now we are going to add the results from DR2, the data release 2, and we see that our results are consistent with our previous results from DESI, and now are at 2.3 distance from the CMB. And that's what we are finding. Now, we could also look at supernovae. In this plot, we marginalize and we have the probability density for omega matter. And in blue, you see the results from our current results for omega matter. And in dashed black line is all results. So they are compatible. And you can see the CMB, which has a higher omega matter value that's preferred in this case. We could now add supernovae data. And what we are seeing is that supernovae data in general prefer even higher omega matter in the Lambda CDM context, depending on the particular value depends on which supernova sample and collaboration data you are using. And because they prefer different value, have different also probability density function, you can have different tensions that ranges from 1.7 to 2.96 against DESI. Now we can now do some expanding the parametric space to do some non-Lambda dark energy model. In this case, omega 0, omega A, called dark matter, and this is the dashed line that you are seeing in this plot. So those lines will be the best fit if you're using this omega 0, omega A model in this case. And this will be, Jonas will talk to you more about that after talking about Lyman-alpha.
So we wanted to highlight one of the main contributions of EFI to this data release is that we collect the bio measurements from the highest resid from the Lyman-alpha forest. We can see here in this slide all the people that are collaborated into that measurement. So for those that are not familiar with the Lyman-alpha forest, the Lyman-alpha forest refers to absorptions in the line of in the light of very distant quasars due to hydrogen in the intergalactic medium. We can see this here in the video, all these different features that appear in the spectra of very distant quasars that are absorbing the light. And we can see that also on the left, on the figures, like for a very low resid, we can barely see these absorptions, but at very high resid, we can see all of them and look like a sort of forest, and that's why it's called Lyman-alpha forest. So using these different absorptions, we can also measure the BO peak. So now instead of computing the typical distance between galaxies, we compute the distance between different absorptions. That is similar to, let's say, clouds in the intergalactic medium of gas, even though that these are not really clouds. So using this data, we measure both the correlation between different absorptions, is what is in the left, towards different line of sight, different quasars, and we measure the BO peak there. And we also do the same for the cross correlation between these different absorptions, the Lyman-alpha forest, and also the quasars that we use to measure it. And we can see in this case that the peak is upside down. This is just because the bias of the Lyman-alpha forest is negative, otherwise it will also be positive. Despite being only a single point at very high resid, what is very interesting is that we measure this point at a resid where the universe was completely matter dominated. So it's like Einstein de universe. And on top of that, the degeneracy between the omega matter and H0 and the sun horizon size at the dark epoch is almost perpendicular to the one that we find with the CMB. So that's why it's very, very complementary to measurements of the CMB. And as you can see, for this resid, we are completely on top of the results from Planck, the one that we measured with DESI. And now we're going to explore the impact of these measurements of the BO peak on the dark energy. So that's the expansion of the universe. As we know, the expansion of the universe is determined by the amount of energy of the different components. So at very high resid, we have radiation that is dominating the energy density of the universe, and at lower resist, mostly matter and dark energy. And here we also have the possibility of having curvature. By combining measurements of the CMB, supernovae, and also the BEO, we can measure the amount of matter, the amount of dark energy, and of radiation in the universe. So within the Lambda quantum matter model, we do that, and we get a best fitting model, for example, just for the BEO data on the top. That is just to the CMB, it will be in black, to just DESI data in orange, and DESI plus CMB in blue. As we can see in the bottom panel, this best fitting model is not able to go through all the points of the measurements from supernova. So this is telling us that within the Lambda quantum matter model, we can describe these two observables at the same time. And we can also see what happens if we do it the other way around. We fit the Lambda CDM model to supernovae and plot the predictions on the top panel now for a BEO. You can also see that this is not compatible. So now, what we find in the end is that the amount of dark energy that we are predicting with the different groups is not compatible. And this is in the end exactly the same as Mark was showing before for omega matter, because within the Lambda quantum matter model, omega lambda is equal to 1 minus omega matter in the case of no curvature. But what happens if we go for a different expansion history that is not like a cosmological constant? In this case, we can have two different models. One that is redshift independent, the amount of dark energy, but omega in the equation of state is different from -1. And then we can also have a model where the amount of the equation of state of dark energy depends with time, as we can see here on the bottom. This omega naught, omega A model. So now when fitting a model with omega different from -1, we can see that we are not able to describe the data. This is the in cyan. But when we do the same, but now using a model with omega naught, omega A, we can see that we can describe both at the same time, the BEO, the CMB, and also the supernovae, that are these red and green lines. So let's see what happens in the parameter space of omega naught, omega A. So just when we are just analyzing DESI data by itself, we are still compatible with a cosmological constant that it will be W naught equal to -1 and WA equals to 0. But when we include the CMB data, we start to see that we are preferring having not a cosmological constant, in this case at 3 sigma. And we also include supernovae data, depending on the supernovae data sample that we use to combine with the CMB and the BEO, we go from almost 3 sigma to 4.2 sigma. So we are starting to reject the Lambda quantum matter model with a lot of significance. And I want to highlight that this is very robust to the type of analysis that we do. For example, on the left is when we, instead of combining with all the CMB data, we only combine with some of the CMB data and not with the late time effects. So the combination is more robust and we find exactly the same. Where we don't use supernovae at very low redshift, that are the ones more discrepant with the BEO data, we are still finding good significance on rejecting the cosmological constant. That is what it will be here in the central panel in brown. And on the right is what we get with, we combine only low redshift proofs without the CMB. In this case, combining with a 3x2 data, and we are still projecting the Lambda quantum matter model. And finally, the physical interpretation of this difference is that now we can see here in the plot for Lambda quantum matter in dash and in blue for omega A, omega naught, omega A. So what happens is that the universe starts to accelerate at an earlier time, and now it has lower acceleration at present time than in the Lambda quantum matter model. And now Mark is going to talk about the implications for the Hubble constant, for the Hubble tension, and also for neutrinos.
Okay, great. So we know that we can measure the Hubble constant at the local universe. And these are several experiments, and one is sure. And here you see H naught for this experiment in green. Also, we can measure the Hubble constant using Lambda CDM model and the CMB measurements. And this gives a lower result for H naught than the local measurements. And here in this plot, you see in pink the contour for the CMB. This has been known for a long time that there is this tension for the Hubble parameter, but now it's going to be more than 5 sigmas, and it's difficult to argue that this is a statistical flaw. So what we can do now is to see how can DESI contribute to this. So the isotropic VAO gives H naught RD as a function of omega matter and omega baryon, and isotropic VAO via Kopachinski gets omega matter. Therefore, if we get the density of baryons from another flow for a priori case, then we can measure H naught. So this is the case now because we can have omega B measured from the Big Bang nucleosynthesis. So this is a paper, that's a recent paper, and we can have the data from the constraints from this. This means that now we have all the dark matter without the baryon contribution, so we can measure H naught. And in this case, what we get is this value. So H naught is 68.51 plus minus 0.58 kilometers per second per megaparsec, and this includes DESI plus PBN. This gives us now a tension. The tension is 4.5 sigma tension we choose. And as we had seen in previous experiments and previous surveys, DESI and clustering of galaxies tends to align with the CMB values, a low value of H naught. So this continues to be the case, and we have to decide what to make of it. Now let's move to the DESI-2 and massive neutrinos. So we know that there are 3 different flavors of neutrinos, each one in correspondence to the charged lepton particle. So we have the electron neutrino, the muon neutrino, the tau neutrino. And these neutrinos, as they travel, they oscillate. And this implies that we have 3 different mass states. So for particle physics experiments, and we know the mass difference between these mass states. And depending on how these mass differences are ordered, we obtain what is called the normal hierarchy or the inverted hierarchy for the masses of neutrinos. So, and in turn, this will give us then the minimum mass that we can have for the neutrinos, which means that neutrinos should have 0.059 electron volts or 0.1 electron volts for the inverted hierarchy. Now what we can see is that neutrinos, we want to constrain the neutrino mass also using cosmology. The neutrino affects cosmology in different ways. One is that neutrino change the algorithm diameter scale to the last scattering because they contribute to the energy density budget of the universe. So the number of the neutrino density is degenerate with omega matter and H naught in these equations that Juan has shown to you. And then we have this degeneracy. In this degeneracy in the CMB, we can see in this plot that plots the sum of neutrino masses to omega matter. In cosmology, we cannot get a particular neutrino mass, but the sum of all of them. So now what we can do is we can, in DESI will measure omega matter basically, and this will constrain on this degeneracy. And therefore, this is the way by making this degeneracy to get a constraint of neutrino masses. Neutrinos, we know the neutrinos are also relativistic at high redshift, non-relativistic at low redshift, and this also changes the power spectrum. But this is not included in this. Here is only through the effect of the VAO. And the algorithm method of the scattering. So once you want to plot the posterior against the maximum probability, what you get is the neutrino masses, look like this. And you can see here in this plot as a function of the sum of the masses in neutrinos. And you can see that basically the inverted hierarchy, it seems to be quite excluded. And then the normal hierarchy is also have low probability in this sense. And curiously enough, the peak of the probability is at the edge of the prior, because we have a prior that says that the mass of neutrinos should be higher than 0. We don't allow for negative masses in this case. So all in all, these give us a 95 confidence level that the mass of the neutrinos is less than 0.064 electron volts. Of course, this is assuming a lambda CDM background. Now, it's worth to notice that if you extend this, the mass of neutrinos to allow for negative masses, this will pick actually negative masses. But this will not make physical sense. Now we can say, oh, let's expand the parameter space to include dark energy. And therefore, this is what you can see here. And this is the case as omega 0, omega 8 cold dark matter. And as a black line, now you get the probability distribution, the posterior for our case. And you see that now with this expansion of the parameters, we have a peak that's above 0. So that's something interesting to notice. And also now the inverted hierarchy and the normal hierarchy are both allowed by these constraints. On top of this plot, you can see also what happens if you add the supernovae data for different possibilities of different collaborations. And now the differences are higher than in the case in which we are on lambda CDM. In all the 3 collaborations give kind of the same constraint. If you want more information, you can also go to the Elber's paper, which is where the mass of the neutrinos is explored.
So finally, we end with the conclusions. So in DESI, not only the DR2, but also DR1 measurement of the BEO peak was the highest precision to this day, and now it is the same for the DR2. And the main result of this analysis is that the combination of DESI-DR2 BEO data, CMB, and supernovae strongly prefer evolving dark energy. So, as we discussed before, we are rejecting the lambda cold dark matter, the cosmological constant, with almost 4 sigma. And with the lambda cold dark matter model, the upper limit for the sum of neutrino masses is 0.064 electron volts. But when we open the parameter space to evolving dark energy, we start to get slightly looser constraints, but the peak of the posterior now is at a positive value. And finally, we want to highlight that DESI has already started a GR5 observations, so a lot of new results are coming soon. Thank you.